Could humans really build a permanent base on Mars by 2030? Our sources have. Well, they have a lot to say about whether that's even feasible. So, for you, our curious listener, we're going to distill a whole stack of articles, research papers, expert notes, really dig into what it means to set up shop on the red planet permanently and self-sufficiently, and, whether that 2030 target is actually within reach.
It's fascinating because when we talk about a human base, it's so much more than just, planting a flag and coming home. It's permanent infrastructure we're talking about. Robust life support, power that keeps running, and this key thing, in-situ resource utilization, basically learning to live off the land on Mars.
Right, using Martian resources.
Exactly, and the ambition behind it is clear, right? It's science, it's human survival becoming multiplanetary, and it's definitely about global leadership in space. But that 2030 date, that's where, looking at the sources, things get pretty complicated.
Okay, so let's unpack that. Our sources seem to paint a really stark picture here. They're basically indicating that establishing a self-sustaining base, specifically by 2030, is, well, highly improbable, bordering on infeasible, really. Now, maybe a human landing later in the 2030s, that seems conceivable, maybe, but a proper base. Agencies like NASA, ESA, even SpaceX, when they talk about a truly self-sustaining colony, they're pointing towards 2050 or maybe even later. So what are the big roadblocks? Why is it so far out?
Right, well, the first one is just physics. You can't argue with orbital mechanics. It's not like hopping on a plane. These optimal launch windows to Mars, they only come around every 26 months.
Every 2 years or so?
Roughly, yeah. Miss it, and you're stuck waiting. And then the trip itself. A typical minimum energy mission, the kind that doesn't require, insane amounts of fuel, takes about 34 months for the round trip. That includes staying on Mars for a while.
34 months, wow.
So think about it. Even if, somehow, a mission blasted off in late 2030, they'd still be flying, or maybe just arriving right at the end of the year. You physically can't establish a base by then.
Okay, so the timing just doesn't work. But let's say we could wave a magic wand and speed that up. There are still huge risks for the crew, aren't there? Our sources really hammer home the radiation issue. It sounds like maybe the single biggest challenge, potentially a killer.
It absolutely is.
Yeah.
Without some major breakthroughs in shielding technology, astronauts on a Mars mission, they could face up to a 50% chance of mortality just from solar particle events and those galactic cosmic rays.
50%. That's chilling. What are we doing about shielding right now? Is anything close?
Not really. Not for this kind of mission. Active shielding, like generating magnetic fields, that's still very much in the early lab stages. TRL 1 or 2, maybe.
Yeah.
And passive shielding, like burying habitats under meters of Martian soil or regolith.
That's
useful, right?
Yeah, use the local dirt.
But the logistics of doing that, digging and covering habitats autonomously with robots on that scale, it's a massive engineering challenge we haven't solved. We're just not there.
So getting there is hard, surviving the trip is hard, but then you need to actually live there for a base, not just visit. That means living off the land, which brings us back to ISRU, right? In-situ resource utilization.
Exactly. Self-sufficiency is the name of the game for a permanent base. ISRU is absolutely critical. Being able to produce, say, oxygen or water on Mars saves launching 8 to 10 times that mass from Earth. Think about that.
That's huge.
It's game-changing. Now, we did have the MOXIE experiment on the Perseverance rover. That was fantastic.
Yeah.
It successfully made a tiny bit of oxygen from the Martian CO2 atmosphere, a real proof of concept.
Okay, so it works on a small scale.
A very small scale, like maybe enough oxygen for a mouse for an hour, scaling that up to the hundreds to thousands of metric tons per year needed for a commercial scale base. It's a monumental leap, like going from lighting a match to powering a city. These systems and the advanced closed-loop life support needed to recycle air and water almost perfectly. They just aren't mature enough. Their technology readiness levels, the TRLs, they're too low for a 2030 mission. Most experts think we need to prove large-scale ISRU works on the moon first.
Okay, so the tech isn't ready. And beyond the tech itself, just the sheer amount of stuff needed seems daunting. Our sources mention needing millions of tons of cargo for a self-sufficient city. Millions. That's hard to even picture.
It really is mind-boggling. Look at Starship, the big hope, right? It aims to land maybe 100, 150 tons on Mars per trip. That's impressive, like a big truck's worth.
But what have we actually landed precisely so far?
Our current demonstrated precision landing capability. We're talking about things like the Perseverance rover. That's about 1 metric ton. Or In-situ, even less. So going from landing a Mini Cooper's weight precisely to landing multiple loaded semi-trucks and eventually millions of tons, the gap is enormous.
And building the base itself, you mentioned robots earlier.
Right. Autonomous habitat construction. It's only at about TRL4, and that's in simulated Earth environments. We are light years away, metaphorically speaking, from having robots build complex habitats on Mars reliably.
Okay, so technology, logistics, scale. It all sounds incredibly complex and difficult, which inevitably brings us to the cost. What kind of money are we talking about?
Staggering amounts. Our sources estimate that a sustained human presence on Mars, you're looking at hundreds of billions, maybe even over $1 trillion over time.
$1 trillion.
Just the first human mission is projected to cost maybe $500 billion. $500 billion. For perspective, the entire Apollo program cost about $280 billion in today's money. This Mars ambition dwarfs that. And history shows us that maintaining that kind of unprecedented funding year after year, decade after decade, it's incredibly challenging politically and economically.
And that's before factoring in the human element, right?
Exactly. You add the fact that there's absolutely no rescue possible from Mars, you are on your own, plus the huge unresolved psychological challenges of keeping a small crew sane and effective during years of isolation. You put all that together, the physics, the radiation, the immature tech, the scale, the cost, the human factors, and you see why a base by 2030 just isn't feasible according to the experts and agencies we've looked at.
So wrapping this up, what does this deep dive tell us about humanity's dream of Mars? It sounds like it's definitely not a no to ever going to Mars.
No, not at all.
But it's a pretty clear no to having a functioning base there by 2030. The path forward, based on what we've seen, seems to be about prioritizing those foundational steps first. Things like better propulsion, making ISRU really work reliably, solving that radiation problem.
And sustained funding, international cooperation. It's a long game.
It really is.
Which I think leaves us with an important question, maybe for you, our listener, to think about. If establishing this permanent human foothold on Mars is truly going to take decades, maybe many decades, what are the most critical foundational steps we absolutely must prioritize right now, today, to make sure future generations actually have a shot at making this incredible vision a reality?